Today we're going to be talking about growth and decay and how that plays into our differential equations. And we have some fun applications today. I'm actually really excited about this lesson. Okay, so our first example here. We want to solve this differential equation. And in the previous video and just in general, I always talk about solving differential equations by separation of variables. So you have dy dx equals 4x times the quantity 2 plus y. Now what you want to get is any term that has a y in it next to your dy, any term that has an x in it next to your dx. So you divide out the 2 plus y and you multiply over the dx. And then you can integrate. The reason I push separation of variables is because 99% of the times when I see a problem on the AP test, it involves separation of variables. Okay, so I integrate to this left side, and that turns into, it's a u substitution, ln of 2 plus y. And then on the right side, you have, oh, that's funny, I didn't integrate it in my notes. This is going to be fun. Okay, so add 1 to your exponent, 1 over your new exponent. Don't forget your plus c. Okay, so now whenever you're solving a differential equation, we need to solve for the y, okay? So writing this as an exponential, ln is e to the 2x squared plus c is equal to 2 plus y. And then I'm going to subtract the 2 over, and I want to talk about something that happens here. Okay, so when you're adding exponents, so when you have a to the m plus n, that's like saying a to the m times a to the n to the n. Okay, so it's like typically we're used to going from same base, multiplying, add the exponents. So I'm adding the exponents here. This turns into this. I don't want to write the same exact thing. This can get rolled into some big constant. I'm going to call it C2 because it's the second constant that I'm using. Actually, no, we'll just call it C. I lied. Let's just call it C. It's technically a different constant. Some teachers might yell at you about that. Send them to me, and I'll say, hey, don't yell at my students. Understanding that algebra is going to be a key part of what we're going to be doing today. Okay, let's get into some applications. The rate of change of y is directly proportional to y. So let's talk about this. Just this simple sentence. This simple sentence is very powerful. The rate of change of y. So dy dt is directly proportional to y. So that's an important differential equation we have here. I'm going to separate out my variables. I use t for a reason. You guys will see here why in a minute. Let's integrate both sides. Once you integrate, don't forget that plus c. Okay, that's really important. On the AP test, you lose, like out of a 5-point question, you'll lose 3 of the 5 points if you don't have that plus c in there. Okay. The absolute values depend on what your initial condition are. I'm going to assume that both y and t are positive because we're talking about exponential growth and decay. So like of organisms growing or money growing, things like that. So I'm going to write this as e to the kt plus c is equal to y. So I'm assuming that y is positive in this case. Remembering what we just talked about, Same base, add the exponents. So this becomes C e to the k t. That should look familiar. Doesn't that look familiar from like exponential growth models? So that's how we get this equation for exponential growth models. Okay, so exponential growth and decay models. Okay, y is differentiable such that y prime equals k times y, and then you have that moves into that differential equation. Okay, if you want to move right into that differential equation, you don't have to prove it each time. Okay, where c is the initial value of y and k is the proportionality constant. This should look familiar from, I teach it in my Algebra 2 class, so you should see it in Algebra 2, you should see it in pre-calculus. Okay, and then talking about exponential growth versus exponential decay, you're growing if k is greater than 0, and you're decaying when k is less than 0, so when that k constant is negative. Okay, let's get into some examples. The rate of change of y is directly proportional. The rate of change of y is directly proportional to y. So I know that I'm starting with this differential equation. Okay, they give me some initial conditions here. They give me an initial condition of 0, 3, 1, 12, and you need to find the value of y when t equals 5. So we know that this, because we just proved it, is that equation. Okay, you don't have to prove it each time. If you want to, you can. If you don't remember it, you can. But now plug in this initial condition. So I have 3 equals c e to the 0 power. Because if t equals 0, that gets me c equal to 3. Okay, so from here I have this equation, y equals 3 e to the k t. Now, remember, this was, if you think of compound interest, okay, there's a compound interest formula. If you had me, it was a principal you put in, e to the kt, principal, what you put in, initial amount, that c is the initial amount, assuming that you're not adding or subtracting anything. Okay, so if you see that right away, you can jump to this equation here. Now you have to do a little bit of work and use this second point they give us. So I put in 12 equals 3 e to the k times 1. E to the k is equal to 4. ln of 4 is equal to k. So now I have my value of k. K is ln of 4. I'm not going to find a decimal for that, just so that I can get the exact value when I plug in 5. When I plug in 5, in my notes, I have 3072. I'm going to double check that in my calculator. I did this a few days ago. Yeah, that actually makes sense. Yep, 3072. Okay, so that's a basic example. Here we have a little bit more of a complex example, where I have an insect population increases according to the law of exponential growth. So I know I have this y equals c e to the kt. There are 250 insects after the third day of an experiment and 400 on the fourth day. Approximately how many were in the original? Oh, so I don't give us the initial c. I give us after the third day, there's 250. After the fourth day, there's 400. Okay, so plug into your equation. 250 equals c e to the kt. T is 3. I don't know why I struggled with that so much. and then plug in your 400 equals CE to the 4T. If you solve both of these for C, this should be a K. I plugged in my T. I was focused on something else. Okay, so I cross multiply here. 250 e to the 4k is equal to 400 e to the 3k. And I'm going to say, I'm going to divide by e to the 3k. So I get e to the k, subtract your exponents, equals 400 over 250. So k then equals the ln of 400 divided by 250. So now I have this equation. Y equals C e to the ln of 400 divided by 250 t. And I'm looking for how many insects were in the original population. So I am looking for when t equals 0. So let's get a decimal approximation for this, for our k. Oh, that is actually a point. So we need to find, so if I need to find my initial population, so I'm kind of looking for C there, you have to use one of these points again. Let's use the first one. So I get 250 is equal to CE to the 0.47 times 3. So solving that equation, we get C, which is our initial condition, remember, 61.036 insects. Now, it says approximately. I would tell you how to round. I would typically say round to the nearest integer, so I would say 61 insects. Okay, Newton's law of cooling. I love this problem. I love this concept. I think it is a really cool application of everything that we're doing. I just love this. It's basically you take a pizza out of the oven, how long until you're able to eat that pizza? That's the idea behind this. Okay? So the rate of change of temperature of an object, okay? So the rate of change of temperature of an object, I'm going to have two T's in here, that's going to be fun, is directly proportional between the difference of the object's temperature and the surrounding medium. Okay, I do that. You're going to plug in a number for that. Okay. Oh, I don't know if you guys could just hear that squeal. That's my cat. She loves Newton's law of cooling as much as I do. Okay, I'm making a stew. When I take the stew off, the temperature is 180 degrees Fahrenheit, the room temperature. So this is that surrounding area that I'm going to be plugging in. After 5 minutes, the stew is cooled to 55. How long will it take to cool the stew until to a serving temperature of 95? So we use our differential equation. Okay, so the big T, the small t, is equal to K T minus my surrounding temperature of 74. Okay, separate out your variables. Woohoo! Maybe I should use a different variable. Now we integrate both sides. Okay, so if I integrate both sides, this left side becomes the ln of t minus 74 equals kt plus c. From here, what I'm going to do is I'm going to plug in my initial condition. So my initial condition at time 0, we have 180 degrees Fahrenheit. So the ln of, hopefully my temperature minus 74 is not going to go negative. So I'm going to say that this is 180 minus 74 without the absolute value signs. K times t is 0. So this is going to get me my C constant. Okay, so let's now plug that back in. So I'm going to carry this on up here. And so now I have the ln of t minus 74. I don't need those absolute value signs. Actually, let me erase that and put in a parenthesis. Because hopefully the temperature is not going to drop below 74. That wouldn't make sense if you think about it. Okay, so now I'm going to solve this for the big T. E to the kt plus ln of 106 is equal to t minus 74. Now remember, same base, adding the exponent. This 106 pops down in front. And I'm going to add the 74 is equal to t. Okay, so now I have an equation. I now need to use this idea of in 5 minutes, we cool to 155. Okay, so I plug in 155 for t is equal to 106 e to the k times 5 plus 74. I solve this for k. I'm not going to go through that. That's a pre-calculus and really an algebra 2 thing. K, I get negative 0.053798. I rounded. Okay, what I actually did in my calculator is I stored that. I pressed the STO button, store that as K, so that I can use that value in future pieces. So now I have this equation. 106 e to the negative 0.053798 t plus 74. Okay, so that's my t. Yep, that makes sense. Now I need to know how long will it take for it to cool to 95. Okay, so I plug in 95 for t, and now I solve this equation. And I solved that equation, and I got 30.09 minutes. And I just love this application, okay? Because you're taking something out of the refrigerator or out of the oven. How long is it until it's a safe temperature for us to eat? How long does it take for your food to cool? Now, it seems like a lot of time for us to cool the stew that we've just made, but I think about it in terms of Thanksgiving dinner. We let the turkey rest, okay, before we eat it because it's been roasting in the oven for so long. Anyway, I'm always thinking about food. Okay, so that is our exponential growth and decay. Please make sure you have everything prepared for class.